And well, today's topic is on rock mechanics, and it was explicitly said in road tunnels. Main thing why road tunnels, maybe it's because we have tunnel systems and choices for different cross sections and systems. So the brief of the presentation today would be some introduction into the tunnel system choices and cross sections that are, so to say, some distinctive feature of road tunnels. Then I will shed a brief light on the scale effects in rock mechanics. I will go a little bit through the rock mass classifications regarding two of the most popular index values, that's RMR and Q value. And then some discussion on the determination of failure modes in tunneling, and then some common failure modes and behavior types. This is something where I'm coming from, so to say, the school of rock mechanics and tunneling. Then something on cross passages, because they are there inevitably in our road tunnels. They are part of the safety concept nowadays. A little bit on the excavation for road tunnels and also on the support elements, because at the end of the day, we look at the rock mass as one of our building materials, but to upgrade, so to say, our building material, we need the support elements. So what is very specific of road tunnels is that we have a cross section where the number of lanes can range from 1 to 4. We can have single or twin tube tunnels, especially when we have twin tube or more, we can have cross passages, and we will have cross passages. And the main thing is that our cross-section geometry depends on the number of lanes, the prescribed lane width, and the ventilation system to some extent. But in general, it's the number of lanes which gives us, so to say, a constraint how large our tunnel is. So just one possible configuration, a road tunnel with one driving lane, one emergency lane, and we will have approximately an excavation width or excavation diameter of 12 meters. So the inner dia will be 10 meters to house all the things we need. And when we look at the areas, we will have about 100 meter square excavation area when we have this so-called flat invert, that we have only abutments for our inner lining. And if we have an invert arch for poorer rock mass, we will end up with something around 112 meters square of excavation area. Now, this twin tunnel, same cross section, will have cross passages also. And I marked here a small word, and that means that is saying varies. I'll come to that later, because the distance between those two tubes has some influence, on the one hand on the costing, because the cross passages get longer. On the other hand, there is rock mechanical implications also. So this is nowadays the standard system how tunnels are being set up. Regardless of the number of lanes, there will be cross passages which connect the tunnels. Now this is a bit different configuration. Now we have 2 lanes and a paved shoulder. So in our excavation width already goes up to 14.5 meters. And the inner dia is around 12.5 meters. And our radius of the top heading just for the excavation is now growing to 8 meters. And then number 3, this is then really huge. 3 lanes, a paved shoulder of 3 meters width. So an expressway in good rock. So we are talking about a larger cross section with 19.4 meters excavation width. And if we have it then really large, so I think that's the largest what is currently being constructed and being planned to be done in India. So that's 4 lanes plus hard shoulder. That's then 202 meters square of excavation area. So this all is road tunnels. And looking at that, it also means that road tunnel is not road tunnel, because such a cross-section of 4 lanes will have different design aspects and boundary conditions than a cross-section with 2 lanes. And that brings me, so to say, on what we look at in tunnel design. We have our underground structure, which may have different sizes. We have our rock mass structure, we have our in situ stresses, and we have our groundwater. So these 3 boundary conditions plus the newly built structure are interacting in many ways. And this, so to say, brings me to the topic of the scale effects. What would it mean for us? And that's why I also pointed out the different configurations. When we look at rock mass, we always have discontinuities. And when we look at the very small scale, we have the intact rock sample. A bit larger, we may encounter in that small area 1 single discontinuity. And the larger we get, the more discontinuities may influence the behavior. And more, so to say, distinct parameters will influence the excavation, the new structure. And there is another thing, that the stability always decreases with the increase of the excavation dimension over the mean discontinuity spacing. So basically, if I have a rock mass with a very wide spacing of discontinuities and a large excavation dimension, the ratio might be the same than a smaller tunnel, but I have a very, very densely spaced discontinuities. Just to have a sort of comparison, because our 2-lane tunnel would fall under the category large tunnel, but in the 4-lane tunnels or 3-lane tunnels, which are constructed nowadays for certain infrastructure projects, we are already tackling the dimensions, especially in width, which are more of a cavern. So the problematics and the tasks will come closer to the ones which we encounter in large caverns. So especially regarding the block failures, that becomes more and more eminent in such large cross sections. So in a nutshell, it means that our cross-section geometries and the scale effects together give a mix, because our road tunnel spans range now from 12 meters to 24 meters width. And this also implies that our underlying rock mechanics, how we look at our rock mass, will not be the same for all the tunnels, and the scale effects have to be looked at. And that is especially important because when there is a design approach for a 10-meter dia tunnel or a rock mass appreciation for a 10-meter tunnel, it will be different than working with a 20+ meter wide tunnel. Now coming to the rock mass classifications, they have also evolved over time. It started with Mr. well, Professor Terzaghi, who made the first rock classification, then Dr. Laufer, then the RQD was, so to say, published, the RMR system came up, the Q system was published the first time. GSI, I put in italics. I will not touch it because that's more a geological system of classification, whereas RMR and Q are really pointed at rock mass classification. So, and basically, when we look at the first classification from Terzaghi, he said, okay, we have a rock condition that can be hard and intact, and then basically we have stratified rock, we have moderately jointed, blocky, very blocky, completely crushed. Then, as a special subdivision, the squeezing rock at moderate depth, squeezing rock at great depth, and swelling rock, which basically means that there must be some chemical or physical process happening apart from the mechanical processes. Now, that class was used for some time. Now, RQD was brought into the picture, and the RQD basically describes how jointed the rock mass is, and then also because only pieces of a certain length are counted. So if the pieces are not larger than 10 centimeters, they are not counted. So basically, every joint set that has a very dense spacing would reduce the rock quality designation. Now, one of the popular systems and very widely used system is the RMR, and this is now coming to a point where several parameters, rock mechanical parameters, are being taken into account. There is a uniaxial compressive strength of the rock, which is taken, of the intact rock, one has to say. There is the RQD value taken into account. The spacing of discontinuities is taken into account. The conditions of the discontinuities is taken into account. The groundwater conditions are taken into account, and, which is quite important, the orientation of discontinuities versus the excavation direction. So, and all these parameters basically are then taken, assessed in the sort of table where we have a test for the uniaxial compressive strength, and with this test result, some values are being assigned to this property. So, core quality, discontinuity spacing, again, if the discontinuities are very, very small, then the points are being reduced. Condition of discontinuities basically means, do we have a gougy filling, or do we have just joints which are dry and rough? Groundwater is being taken into account in the sense that there is a distinction between completely dry and flowing with some subdivisions. And then comes the rating for the discontinuity orientation. And you can see here that it's even subdivided between tunnels and mines, so to say linear underground structures, foundations and slopes. Because later on, many of these rock classification systems were modified. Originally, RMR was coming from the mining industry. So then the rock mass or the rock classes are determined when we take the sum of all the ratings together, and it can be very good rock or very poor rock. So a qualitative description is already there, but taking just the RMR value might not be 100% sufficient for certain effects which we will see later on. But anyway, there is then some meaning attached to it that the stand-up time, which is important for us in tunneling, is being given in terms of span and in terms of time. So that means if I have very good rock, a 15-meter span can stand for 20 years. And in the very poor rock, 30 minutes for 1 meter span. At least there is a range or something qualitative you can take into account. And interestingly, there is then also proposed values or value ranges for the cohesion of the rock mass and for the friction angle. I will come to that later because it means basically I'm taking the input of joint sets, of uniaxial compressive strength, and the water and other things, and these items basically give me equivalent cohesion and friction values, which can be used for a first estimate in a continuum program or for a hand calculation. Then RMR is giving also guidelines how to basically classify discontinuities, again with the ratings, so that is a subdivision. Then very important, the discontinuity strike and dip in terms of tunneling orientation. Usually something that is striking parallel to the tunnel axis is seen as very unfavorable and will cause a lot of headache for the tunnel engineers, whereas so to say driving and cutting through the joints perpendicular to the tunnel axis is not unfavorable. Only in this case when the joint sets are coming inside. But all in all, it's okay and manageable during the driving. And now this is one of the standard, so to say, tables. RMR even, or the founders, the inventors of the RMR, have made a link between excavation and support system and the RMR value. So basically, once I'm having all the data, I'm having RMR ranges, I can estimate the support. Well, I think the most important part is the 10-meter span here. That's also written on the table, because if I have 12-meter span or even 20-meter span, it might be completely different. But this was decided, okay, for a 10-meter span example, this would be what we will take for a support. And the support system is something that is anyway known. We have rock bolts, we have sprayed concrete, and here even steel ribs are put into the table for the very poor rock. Now, this is RMR standing as it is. Now the next very popular system and very widely used system is the Q system, the Rock Tunneling Quality Index, which has now a little bit different input parameters because RQD is still there. There is a joint set number, a joint roughness number, a joint alteration number, joint water reduction factor. So a lot of emphasis is put onto the joints. And the stress reduction factor is also given, which is reflecting certain peculiarities. And for the RMR means that the block size, that means RQD divided by the joint number, is important, and a parameter, the interblock shear strength with the roughness and frictional characteristics of the joint walls or any filling materials. And then the stresses, because the stress reduction factor can take care of loosening loads in case of excavations if we have shear zones, clay-bearing rock stress in the competent rock is taken into account, the squeezing load if we have very incompetent rock. And this joint water coefficient is basically related to the water pressure, because water pressure will have an adverse effect on the shear strength of our joints, because the effective normal stress is reduced. And one thing that came in the Q value is, compared to the RMR, there is this so-called equivalent dimension. This value is basically to establish a bit of a relationship between the Q value and the stability and support requirements of different underground excavations. Now, this is taken directly from the publications, and there is, so to say, this DE, which is the excavation span, diameter or height, whichever is thought to be of importance, and the so-called excavation support ratio. Now, this ratio looks very similar to the ratio which I showed before in the scale effect page, where we basically were comparing excavation span and joint distance. So it's from the same, so to say, line of thinking. And now the Q value knows 5 categories of excavations and gives them excavation support ratios which are different. It goes, so to say, from temporary mine openings, which have relatively high values, to underground nuclear power stations, railway stations, facilities where many people are there, which enjoy, so to say, a higher factor of safety, because by reducing the excavation support ratio, my equivalent dimension will go up. And that is an input to the next design chart, so to say, which is very common for Q value based support estimates. And you can see whatever we are talking about is major road tunnels, and they are all in the category D, which means this excavation support ratio is 1. And many of you will know that chart. I put a question mark in here as a design tool because I still, and many others, see it a bit critical to just take one chart. But at least we have here the span. So that means a 10-meter road tunnel would basically run along this line, whereas the 20-meter span road tunnel would run along this line, which is quite a difference already, and means that the same support system cannot be used with different spans. And with every, so to say, span and Q value of the rock mass, which is shown here along this line, we can go from unsupported to spot bolting, then systematic bolting up to fiber reinforced sprayed concrete, ribs, shotcrete bolting, when it's basically the whole range, what we see in many projects. And then the bolt spacing is also given here as an indicative value from 1 meter to 2.5 meter. So this is a sort of, well, design tool which can be used. Now, for both of these systems, there is a comment from Professor Hudson, and I think this comment is always worthwhile to be called in and into everyone's mind, because the thing is, a Q value or an RMR value is a single number to describe all the complex things which are there in rock and rock mass and ground. So there is, usually this is a good thing when you are in a very early stage of the design or of a project to estimate what will be the efforts, but still for the detailed design there must be a bit more. And you know, this is the comment of Professor Hudson, because the perceived main governing parameters for rock engineering have been included in the RMR and Q system. So remember, Q system is very heavy oriented towards the joint. RMR, joint sets, jointing. RMR is having the uniaxial compressive strength inside. The use must provide some overall guidance. So that is always there. However, the use of these systems as the sole design tool cannot be supported on scientific grounds, because they are so standalone and so specific that it would not be really good to take them alone. So, and then comes an example that the measured values of discontinuity frequency and RQD depend on the direction of measurement. So that means how my drilling is oriented when I take the RQD already gives me some different values. But it's not accounted for or described. Then similarly, the rock mass modulus depends very much on the discontinuity stiffness, and the modulus is anisotropic, but yet there will be only one value. So this is the same with the back calculation or the estimate of cohesion and friction angle from an RMR value. So, and the concluding sentence is basically that the rock mass classification approach will be supplemented by other methods in due course as the correct mechanisms are identified and modeled directly. And I think this is now leading me to a development which is relatively young. Basically 20 years ago, the first publication was done on this Austrian guideline. So to say, that's the short form. The full title is Guideline for the Geotechnical Design of Underground Structures with Conventional Excavation. What is interesting for us from the rock mechanics perspective is basically the ground characterization. What is then coming in this whole guideline, apart from the ground characterization, there is the procedure for the determination of excavation and support during the design phase and the construction phase. So that is, so to say, the objective of this guideline, to provide the procedures that if two people are studying the same tunnel, that they come to more or less the same conclusions. And it lays down the approach to build tunnels from the design to the construction phase, and it's an observational approach. Basically, it means whatever is being assumed in the design phase has to be proven or cross-checked in the construction phase. So the general procedures for these two phases are outlined. Now, interesting for us in terms of rock mechanics is the failure modes of the unsupported underground opening, and they are described broadly what failures can occur. And this ground behavior is determined on the unsupported, fully excavated cross-section. So that means when we look at the ground behavior, we take into account the size of the cross-section. It makes a difference in terms of ground behavior whether we talk about a 10-meter wide tunnel or a 20-meter wide tunnel. And all the other influences which have been already outlined, like the groundwater, like the joint sets, they are all taken in, or shall be taken into account during the determination of the ground behavior. And I think that's one step ahead of all other rock mass classification system, and it's also not really a classification system. It's basically the distinction between behaviors, and the basis for a project-wise classification system that we look at the behavior and not at certain index values. So what are the general categories of ground behavior as they are outlined in this guideline? So there is basically the name or the basic category, and then a qualitative description of the potential failure modes or mechanism during excavation of an unsupported ground. So that means coming from stable, which means that there might be small blocks coming out, but all in all, the ground is stable regardless how we are excavating. Then behavior type 2, which is that there is a potential of discontinuity control block fall, means that my discontinuities are now several sets, and they may form blocks which can come out. Now, already we can have voluminous discontinuity control, gravity-induced falling and sliding of blocks, occasional local shear failure on discontinuities. So basically it means the rock itself is fine, but due to the discontinuities, there might be also larger volumes of rock mass when unsupported, which may go into a movement and may fall out. Then comes the shallow failure. Now, failure means already that something is failing. A failure criterion or strength criterion would come into the picture in this behavior type already. So it's described as a shallow stress-induced failure in combination with discontinuity and gravity-controlled failure. So usually these things are interrelated and can also trigger each other. Another behavior type 4 is called voluminous stress-induced failure. So that means large underground or large ground volumes are failing and large deformation is occurring. So the best example for this is usually a shear zone is running in this behavior type, especially when the material is very, so to say, broken down to very thin pieces and the overburden is high. So very really without any support and even with too light support, displacements in the range of tens of centimeters can occur. Then one rather special behavior type is the rock burst. which is a sudden and violent failure of the rock mass, as if we take a sample of a relatively good rock into the uniaxial compression machine and load it, and don't stop when the rock starts breaking but push further, then this energy is loaded into the sample until it bursts. And this is specifically for highly stressed brittle rocks. And the energy release is relatively fast. That's why it will happen suddenly like a burst. Now one other failure mode, which is very much controlled by discontinuities, is the so-called buckling. This is when we have narrowly spaced discontinuities, and basically the rock behaves like a column, a very slender column, which is buckling out and then breaking. Usually it comes also with shear failures. Now, behavior type 7, crown failure, means basically that there is always the risk that there is an overbreak in the crown, which also leads to a progressive shear failure. I will show 2 examples where this happened, and this is also usually associated with low confining stresses, so that the material is relatively loose. Raveling ground, well, this is basically like soil or like a gravel type behavior. And again, it means that the rock is fractured. It can be dry. Water is not required for that, but it's poorly interlocked and it can ravel, and that has to be controlled. Then comes the flowing ground as a behavior type, where we have fractured rock, which is having a high water contact, and like a soil, it is just flowing out when, so to say, not supported or treated even. Then, interestingly, this is coming up again. Terzaghi already had it, the swelling ground, and it basically describes the time-dependent volume increase by physical chemical reactions, usually in combination with water and stress relief. So that means that would be the swelling rocks like gypsum and other things, which can create over long periods of time a steady increase in the support loading. And this number 11 is something that is, I think, very much applicable also in India. It comes from the Alps, where we are having sometimes frequently changing characteristics, but as young mountains, same will be there in the Himalayas. And this is a combination of several behaviors with strong local variations. So basically, this is when we have block in matrix rock, intact blocks, a very soft matrix, tectonic melanges, etc., which is a very special case, because depending whether the blocks are getting into contact or not, the matrix material may determine the behavior. Now, and this is now where we are coming back to rock mechanics and to strength of material and all the other basic things. How will we get the ground behavior? Because one thing is definitely that we describe it qualitatively, but the next step should be that we need an analytical model or some model to say this is the possible failure of this ground. So there are analytical models which start with the joint or block analysis, with stress assessments and checks against any failure criterion, more Coulomb or a Hooke-Brown model. and other generally accepted, and I made a bracket here, rock mechanical models, because it can be any mechanical model which is generally accepted. And then come the numerical models, which are nowadays very popular and widely used. And we start with a continuum approach, like finite elements, finite differences. And then also in use in rock mechanics is the distinct element method for blocky jointed material. And I've given here some examples because they are the most popular softwares for this method. That's UDEC and TRIDEC. And then one step ahead is the general purpose distinct element methods, which are mainly used for scientific research. That's why I put in this word academia, and this is the so-called particle flow codes. Usually in the engineering practice, not often used, but very powerful methods. Now, coming to blocky rock mass, there is the so-called block theory, as it was coined by Goodman and Shih in 1984. And here we need not so much input to make the first assessment. We need the geometry of our joint sets and the excavation geometry. And then we can already sketch out what would be our key blocks. And these are the ones which are located quite dangerously and may, through gravity, fall out with all the consequences. I mean, here only few key blocks are shown, but it may happen that one key block is falling and the next will follow. So when we look at the ground behavior types, it's mainly connected with the ground behavior type 1 with stable, and ground behavior type 2 where we have block-induced failures. So joint sets are controlling my behavior of the unsupported rock mass. Now coming to the next step, that we basically want to understand what is happening when we do the tunnel, when we take out material. And the easiest approach is to see, okay, we have got a primary stress field and a secondary stress field, and they must be different. And there will be a stress concentration at my excavation boundaries. And usually this would be, in the first approach, a circular excavation where we have, so to say, the excavated tunnel. Here even it shows the deformed tunnel after excavation. And this is, so to say, the tangential stresses which the sidewall and the crown are undergoing. Here the tangential stress is shown and the radial stress, which finally in the sidewall becomes the horizontal stress, and here the tangential stress is based upon the vertical stress, and then it increases. And you can see here one factor is coming in, that's the coefficient of side pressure, which in rock tunneling may vary quite substantially. If we have a tectonically active area, then the K node will go beyond 1. Usually in the first check in a normal rock tunnel, you will come to 0.5 as the usual applied value. Now, intentionally, I put in here also the elliptical opening. First of all, in rock tunnels, we are ending up with something more or less elliptical. And the other thing is also that in the elliptical opening, the two semi-axes and their ratio define the stress levels. substantially. Just switching back to the circular, in the crown and in V invert, the K value, if it falls below 0.3, we may even get tensile stresses in the crown and in the invert. And in the sidewall, the maximum tangential stress with this approach, what we can have here, would be 3 times the vertical stress. Now, when we look at the ellipse and say our width would be 12 meters here, and this A would be, say, 6 meters, then we have here a factor of 2. So that means in the sidewalls, we would have 2 by 2 plus 1. That's 5 minus K. And in the crown and invert, we'll have here 1/2. So that means 2 times K minus 1. So again, now the K can be 0.5, and we have, so to say, no tangential stress here and here. If it's 0.3, we will have already tensile stresses, which is quite important because it shows us that the wider the cross-section gets without having more height, which would be, so to say, extra area to excavate, the more we have to look into the stability here, and the more important it becomes to keep the roof free of any failures. Now, what can we do with this very simple analytical stress assessment? We can check the tangential stresses in the crown and in the sidewalls against uniaxial compressive strength, which is either taken from the lab test for the intact rock, and what is also a possibility is that we check against so-called rock mass parameters, which are much lower, but there we have, so to say, a bit peace of mind that we are definitely on the safer side. Then we can check such an analytical stress assessment against some failure modes associated with layered rock mass. Having said that, also the local check of a shear failure with one joint set can be done. And I mean, I have not put that up. There is a number of formulas which give us the depth of the plastic zone of the overstressed area just for the circular cross-section with different K values. So that means I can cover, in terms of ground behavior types, nearly everything, because 1 and 2 will be just a check whether the rock as such would endure the stresses. 3 would give me already whether there is a plastic zone, how deep it would be. 4, I would get this area which is overloaded. And for the type 6, that is the buckling failure, I can also check with this simple analytical tool. And rock burst, I have to relate then if I take, so to say, my sidewall stresses against what the rock would be able to endure without failing. And it has to be mentioned here, when a rock mass is going beyond a certain stress level, which can be between 75 and 90%, 95% of the UCS, microcracking is starting, and it can be that such a specimen, say, if loaded with 90% of the uniaxial compressive strength, will fail after some minutes, because the procedure of the failure has already started, and there is many or a lot of research in rock mechanics on that. I think some of you might be familiar with the catchword Kaiser effect, that is when this is setting in brittle rock mass. Even before the immediate failure, there will be an effect setting in that there is acoustic emissions, that microcracking is occurring, and that usually would be the announcement that a failure may come, and this failure comes then without any further warning. Now, the different failure states, failure modes, are also connected to stress states, in the sense that, I mean, a tensile failure, very simple, I will have no confinement or very little confinement, but mainly I have got one of my major stresses, of my principal stresses, which becomes negative and becomes, so to say, tensile, and rock mass is not that resistant against tensile loading, so it will crack. So you can see here it's usually a cutoff value because with the normal C5 criterion it cannot be covered. The next failure mode would be the splitting tensile failure, or basically what we see often in the uniaxial compressive stress tests, especially with hard rock, that the rock specimen is splitting up. And then comes, so to say, the shear failure, which is associated with the usual phi-C concept, so to say, cohesion and friction, or more Coulomb. And then comes also the triaxial compression, which is also directly linked to the shear failure. And there we have already not only the principal stress, but also the major principal stress. We have also a minor principal stress. When you look at the uniaxial test, our minor principal stress would be 0. We have no confinement. And one can see a little bit of confinement can give a good increase in the strength in the principal, the major principal axis. And this failure mode is not so interesting for us in many rock masses that would be a structural failure. That's interesting for porous rock masses. Now, coming to the check of the failure mode, what I mentioned earlier, so at this point, the tangential stress is being calculated, and then several failure modes can be looked at. The first thing would be the brittle or the uniaxial compressive strength failure, so to say, what is called splitting tensile failure here. And the other thing would be a shear failure, but the shear failure also, as shown here, requires already a little bit of confinement. And then there was also the mentioning of the buckling failure earlier, and this is something that is overlooked in many places, because if there is a jointing which is running, so to say, parallel to the excavation wall, then we have, so to say, like layers of rock, and we have, in this case, a length, and then the thickness, here denoted as T, of the layer, so to say, the distance of the joints. And this relationship here is basically telling us, okay, when this LSP is the same like the distance between the joint sets, then the full, so to say, cube strength is applicable, the full index strength. But if we have joint sets which are smaller than this length here, this buckling length, so to say, there is a strength reduction. which goes quite fast and may reduce our strength if no measures are taken down to, well, 34% and even less. So it means when there is a layering in the rock mass and the side walls are relatively straight, I mean here the side wall is the example, same can happen also in the invert as shown here, then the rock mass may buckle and fail even under much lesser load than it would endure as intact rock mass. And taking something, so to say, a little bit earlier, here you can see the same thing, like here, but with rock bolts inside. Now each of these rock bolts is basically reducing down the buckling length, and just by, say, reducing the buckling length to half, we would end up from 10 to 5, and our strength would nearly double just by keeping that under control. And this is something very important and one of the reasons why rock bolting is so important. Now, for the crown failures in tunneling, there is two, which is, so to say, the major ones. One is the dome-like failure, where basically still a limited area of the crown is triggering a failure. Basically, this material here, this rock mass, is loosened, is having not much confinement, and then it triggers a fall of this mass here. But in this case still, it is depending on the friction angle, and one has to see one thing. It is assumed that these areas, the side walls, are still intact. So without that assumption, that would move further outward. The next failure, which is common and quite dangerous, that's the chimney-like failure. And that is now something slightly different to the dome, because the chimney failure is really progressing upwards. And as you can see here, the chimney failure is depending on the cohesion, if we have soft ground. And in rock, it's the same thing. If I have no cohesion and maybe not even any side stresses or confining stresses, this may go up fast and a lot of material will come in. And these failures are particularly nasty because working through them takes some time, because we have then some loosened area, some hollow area above our tunnel, which we have to take care of. And I mentioned here it's usually associated with a ground behavior type 7, crown failure. But when we have raveling ground, which is described as a ground which has no cohesion, where the blocks are loose, it can also occur when the failure occurs in the crown area. But raveling ground is more general, so the failure can also cover anything at the face or on the sidewall. Now, this is, so to say, the idea how we can get hold of the failure modes, the ground behavior with analytical and, so to say, back of a napkin type checks. And the next one would be the numerical methods, where we can also assess the ground behavior. Now, as mentioned earlier, the three main types One type I forgot here, that's the boundary elements. They would be here with the finite elements, but they are not so popular nowadays. So I concentrated on that. We have the finite elements. They are basically a continuum analysis. And to be very honest, nowadays you don't need very much experience to start an analysis. The software packages are very user-friendly. So you can enter the geometries, you can enter the parameters in a very user-friendly interface, usually a graphical interface. But still, checks are required always to somehow see whether the result is realistic. That is for all numerical methods. And small remarks I'm giving here, well, jointed and layer materials are introduced in all the modern codes to assess the joint-dependent failure modes, but still, they are not always used. That's the main issue, because you have to get the parameters or assume some parameters for your joint sets. Where the finite elements are a great tool is when we assess interactions between several excavations. That means twin tunnels, because the analytical approach to say that 2 diameter is enough distance to have a stable system is sometimes right, but sometimes it can prove not so right, and then we need much more distance between the 2 tunnels. Then the next numerical method used in rock mechanics is basically the distinct element method. It was developed for blocky and jointed materials. It has a discontinuum approach. Here we need already some experience and also the joint parameters. Some reliable parameters should be there. And as mentioned before, for jointed and blocky rock mass, this is a very realistic approach, but it's not as popular as the continuum approaches. So when you see projects, many people are using the standard softwares from the finite element or finite difference method. And now, as I said earlier, there is the general purpose distinct element modeling, which is relying on contact mechanics. So the user must be familiar with the modeling and the background. And that's why the circle of people using that systems is relatively limited. And it's used mainly in investigations. And one very distinct element of this method is you simulate from nanoscale up to large-scale models. So you can simulate the development of a shear failure into a specimen. You can simulate block fall rock mining. It's possible. So here the scale effect can be taken care of. So as I said, finite element, finite different approaches are the most popular ones, but one caveat is there from the rock mechanics, because when we look at the research in rock mechanics and what is also driving failures or instabilities, that's usually the joint sets. And when we then go to the modeling with finite elements, we are going into a continuum modeling. So rock mass is not a continuum, and especially when we have strength parameters which are derived through index values. As you may remember, the RMR gives some proposed parameters. These values need to be checked very, very critically when we are determining the ground behavior, because basically we have taken our strength of the rock mass, we have taken the joint sets, mixed everything together, then we shaked it a little bit, and then we are doing a finite element calculation and say this is the ground behavior. This needs to be reviewed always. Then one thing, if we are using 2-dimensional codes, the usual plane strain codes. We shall never forget we model something that is infinitely long. So having this in mind, anything that has to do with intersections has to be approached differently. Then the modeling of faults. Shall we use a joint? That means an interface element, or shall we model a fault discretely? Means that we take really elements and associate them with very low values of strength. Again, the 2D effects need to be seen in that also. If the program allows you to introduce joint sets, please make a trial to see the effect. Sometimes it's an eye-opener to just take the main joint sets and put them into such a program. And as I mentioned before, make a napkin assessment. Really very rough to see whether these things can really happen. All these modeling approaches are very good, but a little bit of cross-checking is required because small mistakes can have big effects. And now some real ground failures to see what it looks like. And when you look at the material, here we have several hundred meters of overburden, but this is blocky and quite loose material, and it was basically a contact zone material or around a contact zone. Whether this is a dome or chimney type failure cannot be said at this point because the face is closed with muck. Another failure of the same type, here it's very clear a chimney failure, and one can see it must be some challenging ground condition because lining stress controllers are introduced. There is also quite a good number of rock bolts seen here. So this is already the stage where this, so to say, gravel heap was covered with wire mesh, ready to be sprayed, then grouted, and then, so to say, excavated slowly. First this is stabilized, and then the void is also being filled to have always this three-dimensional stress state. So, and it seems that this loose and blocky rock mass could not be held in the limited area where it came through the support, and then this chimney type is going up very quickly. And again, you see a few major blocks, but the rest looks like gravel, which has come in. Now, I'm jumping, so to say, to the cross passages, because they are always there and they need to get some attention. I mean, first of all, they are usually excavated when both the tunnel tubes have been excavated. That's the usual way of doing it. Only in some cases, they are done as an access to a starting point of a new drive, but that is really a special case and needs to be seen separately. And there is one thing, the cross passages again change the stress state after 2 tunnel drives. So we have another stress state, and this stress state we cannot replicate with a normal plane strain analysis. So this is now a 3-dimensional stress state, and there is some influence onto the existing tunnels also, especially when the distance between the tunnels is very low and the rock mass is weak. So I mean, this is a scheme, so to say, of the elastic stresses. We have our tunnel number 1, we have the tunnel number 2, and in between we want to do a cross passage around both tunnel tubes in the area where we, so to say, enter into the cross passage. We have already a changed stress state. And now we are going, so to say, through this material, which is, in the elastic case, having elevated stresses. if the material has been overloaded, we are going through rock mass which is not as good as it was before. And when we look at this in a sort of layout, this is now for a K-Note 1 elastic case. So whatever you can see right here would be double the initial stress. Now we are entering here. So in these corners, we are not talking about doubling. We are talking about the doubling of the doubling, so to say. So we have 4 times theoretically, and in the elastic case, the stresses compared to the in situ stress. So, and in some cases, this will be too much. And it also gives the reason why the corners and edges of cross passages usually require and deserve some more consideration, that there will be some additional support which has to be taken. So from the support point of view, the cross passages need to be designed for an increased stress level. Also, we have to see that the initial section, the starting of the cross section, may go through broken rock mass. So it's weaker than we have earlier experienced in the main tunnel drive. So when we have the phase mapping from the main tunnel, first of all, we have 90 degrees of direction, which has an impact on our jointing. And then we have all the other stress changes which happened. So basically, in many cases, we do a four-poling for the cross passage. We may even need phase support in the cross passage, especially in the starting area. And all these edges will have a considerable stress increase. And during construction, so that's basically the practical thing, if the shifting of cross passages is possible from a locally weaker ground to something more competent, then usually it's being taken into consideration because it mitigates several problems. So now, coming to another thing that is influenced by rock mechanics and that influences also the behavior of the rock mass is the excavation. So basically the subdivision of my face. I mean, usually because of the size of the cross section, we cannot excavate full face. Or because of logistics, the tunnel is too high. Then sometimes the top heading is further subdivided depending on the ground condition and the cross section width. You may imagine that a cross section with 20 meters or 18 meters width cannot be excavated in one go. Or it can be excavated in one go, but it might be a bit unpractical. Because it's also determined by the logistics, what I can do. Taking one blast is fine, but if I'm having then 200 cubic meters or 300 cubic meters of material, I have to get that out. And then comes another point in, that is this so-called stand-up time model. The more time I'm losing with the mucking, the more time I'm having a completely unsupported cross-section. So the poorer the rock comes, the smaller I try to make my cross-section, which I'm opening in one go, I have to say. Not the overall cross-section, but what is opened in one go. And as it's written here, the support should be introduced as soon as possible. So these two drawings are more or less in the same scale. A 2-lane road tunnel and a road tunnel with, I think, 4 lanes. The width is double. The height has been tried to be kept as low as possible somehow. But you can see here, there is a face bolting already shown in this support drawing, a relatively dense pattern of rock bolts. Even 4 poles are shown here. So that means for this support class, the rock mass quality expected is not so good. We have to stabilize the face, and we'll go with the top heading and the bench separately, and later on with the ingot excavation. Now this, just by looking at it, and the bolting pattern looks like it is better rock mass, but due to the size, there was a subdivision in different pieces of the top heading. So, and this is now a technology which is more or less associated usually with caverns, like also in some rock caverns, where usually a pilot is made and then the side slashings are coming, depending on how the contractor is comfortable. Usually such a large cross-section can only be done in good rock with that support as it's shown. So logistics become an influencing factor how you subdivide your cross-section. So let's say this is a tunnel where the support has a major role, and this here is an underground quarry where the support is keeping the, so to say, excavation boundary intact. Now, coming to the ground support interaction. So we are now one step from the behavior type of the unsupported excavation coming to the supported excavation. And that means we have an interaction between our ground, between our rock mass and the support. And this is the very famous Fenner-Bacher curve. In some places, it's called the convergence curve. It's the same. It is basically showing when we have the initial stress, so to say, the virgin stress field, we have a point, and then we are, so to say, coming down with the inner stress in this circular opening to 0. Now 2 curves are there. This one would be the elastic curve, this straight line. And this one is the curve when the material is elastoplastic. This here would be the theoretical continuation when it's really elastoplastic. But in reality, usually, since the rock mass disintegrates and exerts then some extra pressure onto the support, there would be an increase in this curve, which is basically due to the rock mass settling upon the support because of loosening. And here is the reaction curve, the support curve. In this diagram, you can even see that there is a small kink here, which means that the support might have been overloaded or might not have been introduced properly, so that there was some local failure. The support pressure drops, then picks up again, and is meeting the ground curve, so to say, again. And once these two intersect, we have a stable equilibrium. That's, so to say, the message of this whole diagram. What can be seen here is that there is a component of time also inside, because support, especially when it's just young sprayed concrete, will not give much support pressure. But once the Young's modulus is increasing, the strength is increasing, this strength will also increase over time. And the loading will increase over time because we are moving on, and that can be best explained by this, it's called theoretical characteristic line, because the convergence is basically a load-inducing constraint. In the virgin ground, all our stresses are initial stresses, and then when we have an excavation, the stresses around this boundary will become less and less. And even at the face, we have already about 50% of the displacement. Well, in elastic calculation, it's about 50%. When the face is not stable or it's very soft material at the face, then this can go higher up. So that means this advanced displacements, which we see in a finite element calculation, but what we cannot monitor in the field, increases. And that means also that this area here cannot take any loads. And basically, when we take this cross section here, where the inner support pressure is 0, this would be this typical cross section where we would analyze the ground behavior type without any support. But this curve will only look like this if there is adequate support or the excavation is totally stable. And that basically leads now to the next subtopic here, and our last one, and that's the common support elements for rock tunnels, because basically rock is one part of the building material and the other part of the building material set is my support elements. So the main support elements will be rock bolting, and I put into brackets here that it's usually used in a systematic manner, or systematic rock bolting as it is called. It's coming in a pattern. And the different types of rock bolts, you may know them. We have the SN type, which is fully grouted, the SD type, which is fully grouted, and the Swellex, which is working basically on friction and is very popular for stabilizing single blocks and is used mainly when we have hard rock and good rock mass. Then we have the sprayed concrete with or without fibers as one support element. And then in advance, we have four-poling as an advance, so to say, support. We have then face bolting, and in very challenging ground condition, we have lining stress controllers now in the kitty of support elements for rock tunnels. And you might have seen there is no steel ribs, no lattice girders mentioned here, because I would consider lattice girder steel ribs as part of the sprayed concrete shell and putting the emphasis on the sprayed concrete. So the steel ribs actually will not take or will not have much influence. They can take load later on, but when it comes to the rock tunneling, the sprayed concrete is very important, and it's pointed out later on why. So one thing why this systematic bolting is very important, and that is because it can maintain the triaxial stress state. Not actually at the boundary, but a little bit inside. When you look at this small, so to say, scheme, this is how it would work. We have a piece of rock which is undergoing some compressive loading, but since in this area there is a rock bolt, the rock bolt is giving some confinement. And what you can see here, that's so to say a testing arrangement. The testing was done beginning of the 80s, that a concrete block with different grades of reinforcement, one can say, so the ratio of the area of the bolts and the area of the concrete was changing. And this is then the results of these tests. So this is completely unreinforced, so to say, the plain concrete. It may reach up to 220 old units, kilopond per centimeter square. And with some reinforcement, so to say, and this is the ratio between the areas, it will come up beyond 300. And then again, close to 400 with even denser spacing of these steel, modeled steel bolts. So that means that when we do a systematic bolting, we are reinforcing the rock mass like a structural engineer is reinforcing the concrete. And the effect is that the bolts exert a confining pressure. They prevent the loosening of the rock mass. If the rock mass is already somewhat damaged, then still it helps to keep this together and prevent any, so to say, exponential failure. And that's why rock bolts are giving us very good, so to say, improvement of our ground condition. And just when you think of a blocky rock mass, which is having relatively fresh joints, so there is a friction inside, but if that is not held together, it will be like a gravel and will settle upon the support. If you put rock bolts into such a rock mass, due to the confinement, I can mobilize also the friction resistance between the blocks, and it will help me to basically, how shall I put it, to basically animate the rock mass here to take some load. And in layered rock mass, as it is happening sometimes, the rock bolting may look a little bit different, to basically see that the rock bolts are as perpendicular as anyhow possible compared to the
I'm not sure I understand.
Compared to the layering of the rock mass, to the rock mass layers. And here especially can be seen that this helps a lot to improve the stability here, because this is relatively thin layering. So if there is a stress which is going along this area, then this may fail first. And if it's even further finer layered, then it may buckle out. Same here. Now, coming to the sprayed concrete as a support element, I mentioned it, it is quite an important primary support element, because when we apply it very quickly after the excavation, it smoothens the surface. That's one thing. So that means we have a smoother surface, no stress concentrations, and it also seals some cracks. That means stress propagation or crack propagation is also stopped. So basically it's a sealing which delays the deterioration of the rock mass. Then also loose smaller blocks will be held in place, because the sprayed concrete has enough shear resistance to keep smaller blocks in place. And now next step, so to say, would be that we look at the circular geometry, and this is one of the standard formulas, this vessel formula, that we say when we have a nice rounded shape and a sprayed concrete liner, then the concrete the sprayed concrete lining is loaded in normal direction with normal forces. But these normal forces are then, so to say, translated into a support pressure, which keeps or exerts a confining pressure onto the rock mass, like we would have a triaxial test in comparison to a uniaxial test. When we have a uniaxial test, there is no confining pressure, and a sample will fail earlier. If we have even a little bit of confining stress, our sample will take more load in the other direction. So this is why early spraying of the primary support lining is very important, and it's basically this rock mechanics principle that we need a confining stress. So waiting and later on putting something heavy is also working, but I will need much more support, and I may have already detrimental loosening all over. Now coming to the four-poling. Four-poling is mainly installed in the longitudinal direction, and it's installed prior to the excavation, very important, and it shall shorten the free span of the unsupported excavation surface. So when you look at this diagram here, we are taking one round out. We don't have any four-poling, so that means if there is a material that can loosen, it may loosen and we have an overbreak, which is quite different than the theoretical excavation line. I mean, this is in rock and in relatively good rock. In soil, this would not look like this, but it may develop a chimney. Now with the four-poling, I'm having, so to say, a geometrical confinement, and the free span, which was earlier this direction, is now being translated to be the free span between the four poles. And the overbreak will be much less. Next thing, again for the stability, is the face bolting. So it means that we are putting in horizontal or more or less horizontal rock bolts into our excavation phase and basically create a triaxial stress state in the face. If not, it could happen that we have first a shear failure of the face because it may slip out, slide out, and then after that, a chimney may also come up. A chimney or a dome-like failure. And usually these two measures, the face bolting and the four-poling, are going together, because if you can imagine this here, and we would have the face bolts going in further here. Here we are. If I'm having here the face bolts, that does not like me. Sorry, the drawing is not really working. I have to go with a pointer. Please imagine here that there is face bolts like in the other drawing, and there is some load coming onto this four-poling. Part of the load can be transferred into the shotcrete shell here, also with the help of this beam, but usually it would be the sprayed concrete who will have to take the loads, and part of the loads are taken by the face. And if the face has a proper, so to say, confinement, it can take these loads coming from the 4 poles. And with that, I'm also controlling a little bit the loosening of the ground and the loosening around the tunnel in this area here. It's something you will not see, but when you're driving, as I've shown in the convergence curve, there is something going on in the face always. And if the face is overloaded, this can take the boundary also already and damage it. Now, the last thing which is in this presentation, and that's the lining stress controllers. Now, the idea can be best explained on this diagram, which I took from a paper from Professor Schubert from Graz. We have our ground reaction curve, as we may call it, the Fenner-Bacher curve, and we have the reaction of the support. Now here, 2 types of support are shown. A support which would be open gaps, so that means that there is real actual gaps in the sprayed concrete lining and rock bolts. And the other line is this one here, which is with lining stress controllers, which are located at these positions instead of completely open gaps. And basically the issue is, if we have squeezing ground conditions, then usually the rock mass may trigger much more strain than a normal support may be able to endure. So sprayed concrete will go up to 1%, maximum 2% strain, and then we have taken all the reserves. Because these reserves are the early creeping, the development of strength and resistance of the sprayed concrete, but a young sprayed concrete can endure some strain, much more than a normal concrete can do. But also there are limits. And if I have elements which basically allow more deformation, my support reaction will look like this. And when these elements are kicking in, they are usually designed to keep a very constant level of resistance so that the sprayed concrete is not overloaded. And they also intersect our ground reaction. If we would have something very stiff, which would go up to here, but the strength would be only this much, it may break, and the rock mass will still deform, and we would not have reached our objective. If we open gaps, we cannot utilize the sprayed concrete properly, because the open gaps cannot transfer any loads. And now how these things will look like in practice, you can see it here. This is one row of these lining stress controllers. Here is even a second row. So this is actually a road tunnel, the second tube of the Tawan tunnel. And you can see here also that the bolting pattern is quite dense. So it has been prepared already for major displacements. And what cannot be seen here clearly, only maybe you can see here a little bit that the anchor plate of this rock bolt looks to be, so to say, in the air. It's not in the air. There is sometimes, as a first measure, when there is larger deformations, you can put 2 steel pipes basically between the sprayed concrete and the plate, the face plate. And this also acts like a so to say, rock bolt stress controller, because first the two tubes have to be crushed and then the full load will come onto the plate. So this is when we expect high deformations. And this is a different system of lining stress controllers, which is also used in Europe, which is having the pipes lying and being, so to say, compressed, and the resistance is increasing steadily over time. At the same time, our sprayed concrete also gains strength and resistance. So I hope that I could give you a little bit of a glimpse into the rock mechanics and also support technology for road tunnels. I'm fully aware that this is only the beginning, because each of the subtopics can be the subject of a separate session. But I think the main points I could deliver. And if there are any questions, please feel free to ask.
Okay, am I audible?
Yes, sir.
Okay. So it was a very nice lecture, Dr. Krenn, and in fact, you started with the basic fundamentals right from scale effects. Then you talk about the classification systems. You touched every part of the process which the tunnel engineers has to go through. And for me, it has been a very, very interesting lecture. Means right from you took the roads, then excavation dimensions, then classification techniques, then you talk about the guidelines also, which were first published in 2001, and how we actually go for the ground conditions, and then how to get the ground behavior. Then also you touch upon block theory. Everything I think you have touched, and it has been a very interesting lecture. And I think we can allow 1 or 2 questions, because then it is already 5 o'clock. We are going to close it. So there is one question by Mr. Roop Kishore. Can you please explain the method to calculate Q value for TBM and utilization? So can you, Dr. Krenn, can you elaborate on it?
Oh my God. I was not prepared for such a question, because I have to tell you very frankly, I'm not very much into the Q value, especially for the TBMs. I know that there is certain developments also in ITA on trying to go with the Q value into the TBM tunneling. But again, it's the same thing like with the, say, conventional tunneling, that taking just the index value might be too less. It might be good for some checks, but for example, when you're using a TBM, your abrasivity will be of highest importance for you. But that value is found nowhere in the Q system, and because it's not there, it was not meant for that. So I would really say going for major decisions, especially when it comes then to TBM, which are a heavy investment, I would not rely on one index value. And I think even people like Jan Knecht, who are the experts in that, they are not relying on one value. They want to see the rock mass structure, because the rock mass structure and the driving direction can be even more important in the TBM drive. And abrasivity and other parameters, which are definitely more important than, say, some joint spacing in this particular case. So I think it is maybe a bit premature to put every index value like a template onto different problem settings. They were also developed in a different context, the Q value and the RMR.
Okay. So I think there must be many questions with the participants, and I request them that they can directly contact Dr. Krenn. And so because we have to close, and on behalf of the ISRM Indian group, I thank Dr. Florian Krenn for very comprehensive, as written by Mr. Mandal. That is a very comprehensive, very informative and interesting and useful lecture. And especially I find that the students will get very much benefited. Not only students, practitioners also will get very much benefited. So I thank you very much. And now I hand over the floor to the organizers. They want to say something. Yeah.
Thank you, Dr. Florian, for sparing your valuable time and sharing your experiences with the research student professionals who are involved with the rock mechanics engineering, particularly with regards to the field development and field experiences. We are really grateful to you, sir. And now participants can send their questions to the secretariat at sunil@cbip.org. We will try to get their answers from the speaker and revert back to them directly. Since we are having a next meeting scheduled for the ISRM governing board, so I request everybody to bear with us, and we will close this meeting.
Thank you,
Thank
Dr.
you very much. Thank you very much. Thank you.
Okay. Thank you and bye.
Thank you, sir. Thank you.
Thank you very much.
Welcome.